say it gives me intense pleasure to know more about the genetics of the land snail, Cypea nemoralis, in 20 mountains in the Pyrenees than anybody else in the world. Now that really gives me a great deal of smug self-satisfaction. I've never admitted that before, but it is true. And that I think actually is that it's like being a really good train spotter, having seen them all. Once you've done that, there's really nothing else to live for. And that's a bit the way I feel about doing research.
Steve Jones is Professor of Genetics at University College London. In 1991, he gave the Reith Lectures on BBC Radio. He writes a regular, often provocative science column for the Daily Telegraph and is the prize-winning author of The Language of the Genes. Professor Jones' 7 wonders of the world include Greek architecture and sex.
My first wonder is summarised by one of those words that biologists don't like to use, an 8-letter word. It's an 8-letter word, a bit like bottom, not to be used in mixed company. Creation. Now, I use that in 2 senses. I get away with it because I'm actually very fond of a piece of music by Haydn, which is called The Creation. It's a great piece of music. It's about the biblical story of the origin of life. But I'm also very interested in the fact of the origin of life itself, which is an incredible wonder, because without it there wouldn't be any biology, let alone any biologists. One thing we know for sure about the primeval soup, it must have been minestrone. It was full of lumps, and the lumps are what make life interesting. Why do I have a passion for snails and slugs? Well, why not? I defy anybody to look at a slug and not see that it's a thing of beauty if you look at it carefully enough. In southern Europe they go into wild displays of colour. There are cream ones and red ones and greenish ones and yellow ones, ones with stripes, ones with spots. I mean, my God, it's like taking lysergic acid down there. It's extraordinary. And they're really very, very pretty if you just sit and look at them. There's one in the States which I really like, which is called the banana slug. And that, as you can imagine, it's about 7 inches long and it's bright yellow and it looks like a crawling banana. Now, I defy anybody not to be awestruck by such a thing. Generally, slugs are pretty conventional in their mating patterns, so you wouldn't think so if you look at them actually doing it in the wild. Some of them hang from great strings of slime from trees and swing back and forth, 2 slugs together in a great cocoon, and probe each other with their mutual penises, trying to decide which one's going to be boy and which one's girl. And it's kind of an alarming thing to see. But, nevertheless, although it may not look it, it's actually pretty conventional. At least I think it's pretty conventional. I don't know whether you do or not. What's much less conventional is to find one slug doing it to itself. Now, every slug is simultaneously male and female, so what some individuals do is not bother with this second person. They suddenly have this bright idea saying, hey, I'm boy and I'm girl, I'll do it to myself. So they insert their own penis into their own female bit and self-fertilize and lay eggs. The thing which is astonishing about sex is that it's there in the first place, given that it's so expensive. I mean, why does any woman bother? Why does she bother to find a man? And having found a man, why does she allow that man to use her and all her efforts to pass on copies of his genes? When you think about it, males are more or less useless. What do? They don't have children. And the whole point of being alive, if you believe in evolution, is to have children, to pass on your genes. Now, the males certainly pass on their genes, they get all the benefits, but they don't get any of the costs. So they're sort of parasites on females. And the big question is, first of all, where do the males come from? Who first had this smart idea of passing on their genes without looking for it? And secondly, why do the females allow them to get away with it? It's completely baffling. Why isn't the world all female? One way of defining what sex is, to make it more boring sounding, is to call it recombination. By recombination we mean shuffling the genes that people or plants or snails have into different combinations, different sets. It's like having a hand of cards, and every generation you do a shuffle. So the next generation gets a new combination compared to what was in the last generation. And that's basically what sex is. So you can see that sex is doing something fairly fundamental. An asexual organism passes on the same hand of cards every time. Every individual is identical. But you're still left with the question, why is that so important? Why does everybody have to be different? Because it incurs an enormous cost. There's a couple of ideas, one of which is popular nowadays, which is that sex is an escape from disease, that all creatures, plants and animals, are constantly being attacked by diseases, by parasites. And in order to escape from them, they have to evolve. They have to change, so they have to change very quickly so the parasites can't catch up with them and kill every member of that species. And the way they do it, it's said, is by sex. Everybody's heard about the Irish potato famine, which was a great disaster. It led to a 50% drop in the population of Ireland.
On the undersurface of the leaves of blighted plants, there is a fine white growth of mould. Examined under the microscope, this is seen as a delicate fungus, named by the botanist Phytophthora infestans.
Every potato in Ireland at that time was in fact the identical twin of every other one. They all had exactly the same genes. They were asexual. They just cut the potatoes in half and replanted them, and so the system went on. And that worked fine. It was tremendously productive until 1 year when suddenly there was a change in the parasites, the fungi that attack potatoes. And every single one of those asexual potatoes, tens of millions of them, turned out to carry a gene that made them susceptible to this new type among the parasites. And every single one of the potatoes just died. That was the potato blight and the famine. Now, if the potatoes hadn't been asexual, or if there had been lots of different varieties, that wouldn't have happened. A few of them might have died, but some would have survived. Once sex gets going, you get incredible amounts of diversity, and the parasites have to struggle to keep up. Once your feet slip in the race against the parasites, then you're done for. Everybody dies. That may be why sex is there. There aren't many rules in sex, but one of them is that the tropics are much sexier places than the Arctic and the Antarctic. If you look at plants and animals in the tropics, they're all basically at it all the time. If you go to somewhere like Sweden, in spite of the rumours, there really isn't much sex going on at all. If you look at a Swedish forest, or a Swedish garden, or some Swedish snails and slugs, you basically find they're trying their best to give up sex. They're either hermaphrodites, both male and female, and self-fertilizing, that's mating with themselves, or they're completely asexual, they're just producing clonal copies of themselves. Not like that in Mexico, I can tell you. It's constant sex day and night. And the reason for that may well be that there are indeed lots more parasites in the tropics. So in the tropics you have to evolve fast, you have to keep running to stay in the same place, and the only way you can do that is by getting hot and steamy and having sex all the time, however expensive it might be. Next wonder of the world. It's got a name that fits. It's called the Miraculous Net, or to use the Latin, the Rete Mirabili. Before I became a student, I worked for a year in a power station, and I had various humble jobs. And one of them was always to go and clean the connie, it was called, in Liverpool. Go and clean the connie. I used to get into this horrible thing full of soot, lots of pipes. I used to have to creep between and chip it off. And it was a disgusting job. And after a few months, I discovered that connie stood for economizer. And what an economizer is in fact an example of this miraculous net, which is what's technically known as a countercurrent system. It's very simple, it's a very simple idea, but it works unbelievably well. What you do in a power station is, what you want to do, of course, is to keep as much heat in the station as possible. You don't want to lose heat, because heat's expensive to make. So the way you do it is, as the exhaust gases, which are very hot, come off the furnace, they're passed through pipes parallel to, but flowing in the opposite direction, to the cold water as it comes in. And the heat leaves the gas and joins the water flowing in the opposite direction and heats it up. Now, it's an incredibly simple idea, but it's fantastically efficient. In a good economizer, you're saving way up in the 90% of heat at no cost. You haven't got any machinery. All you've got are these two pipes with liquids flowing, or gas in one direction, liquid flowing in the other. And I remember thinking that was pretty neat in spite of all the mess, which I had to clean out. But I was astonished to find, when I started doing biology, that exactly the same pattern, even more efficiently, has evolved again and again in the living world. The most familiar, perhaps, is in the legs of wading birds. I used to be a bit of a bird watcher. I used to go out into the Dee estuary and look at birds in February, which is a good time to do it. And my feet now and again used to get wet in the sea, and I used to get bloody freezing. But the birds didn't seem to bother. Didn't seem to bother them at all. And that's because they have a little economizer system in the tops of their legs. What happens is that the blood vessels bearing the warm blood, leaving the body, and the cold blood, freezing cold blood coming back from the feet, run next to each other. The warm blood goes out, the cold blood comes in, and just like the power station, the heat is, with incredible efficiency, retained in the core of the body. The heat leaves the warm blood and gets into the cold blood and never gets to the legs at all. The beautiful thing about the Miraculous Net is that it shows the efficiency of evolution in producing wonderful designs without a designer. The bird is faced with just the same problem as the design engineer, and it produces just the same solution, but it does it not with a slide rule, but by evolution. So my next wonder is the rules of Greek architecture. And that's got kind of a personal tinge for me too, because like many scientists, although I admit it and most others don't, I have both a dislike and a fear of mathematics. And I'm not very good at it. In fact, I'm, to be frank, rather bad at it, which is particularly unfortunate in my kind of genetics, which is called population genetics, which is actually a very mathematical subject. There's a phrase I sometimes use. Somebody once asked me, well, what do you do when you come across an equation in a scientific paper? When you've been reading it, you look at this equation, and I say, well, I hum it. I assume that the person who wrote it down knows what it means and got it right, and I'm willing to take that on trust, which is a terrible admission, but I'm willing to admit it. And one of the few occasions I managed to escape from that was at school when I was doing a maths class, and we dissected the mathematics of the Parthenon. If you glance at the Parthenon, it looks like a big square town hall-y kind of building. In fact, there's not a single straight line in it. It looks square, but it's not. The base of the Parthenon is several hundred feet long, but in fact it's not a straight line. It's a very, very subtle curve. It's a curve with a radius of about 4 miles. The center is only an inch or so higher than either end. And if you look again at the columns, there's all kinds of hidden mathematical subtleties in them. They're not, in fact, space equidistant from each other, and that helps with the perspective. What's more, they're not actually upright. Each one of those massive columns, and they're huge things, leans in by about 1.5 inches. And if you project them upwards into the air, they'd actually come to a point at a place about 1.5 miles up in the sky. The sides of the columns are not actually straight. They're minutely curved. They're like a very, very subtly graded cigar. They're fatter in the middle than at either end. And that, it turns out, helps with the perspective. It makes them look straight when you look up at them. And there's been some argument about what the curve is, but many people believe that it's a very precise curve we now know well, which is years of engineering, which is called the catenary curve, which is the kind of curve a chain or any object with weight takes when it's suspended by the ends. And that, of course, is the kind of curve which, shall we say, the Forth Road Bridge takes. And everybody agrees that's actually rather a pleasing object. We like the catenary curve. Lo and behold, 2,500 years ago, an extraordinarily subtle curve of that kind is in the Parthenon. So all that's pretty good fun, but in fact, if you walk around any British city, you see miniature Greek temples everywhere. If you look at my house in Camden Town, you can see when you look at it, it's slightly odd. It's got 3 stories, but the ground story is covered in stucco, and then the other 2 stories aren't the same height. And there's a rule behind that, and the rule is the same rule as in a temple, because the ground floor is in fact the podium of the temple. One is supposed to imagine that there are pillars in between the windows on the first floor, and the top floor represents the frieze with all those dancing satyrs and so on in a real Greek temple. And the proportions are just the same as they ought to be for a temple. You can see in a very grand house it would still have those great grand stucco pillars. Well, by the time they got to build this one, about 1850, they'd run out of money. So you had to imagine the pillars. But the proportions are still there. And I think the fact that those proportions persisted for really 3,000 years and are still pleasing, are still at the basis of all classical architecture, says something very deep about them. They're actually speaking to us about what looks good, what makes sense. And that's why I like Georgian houses, and that's why I like Greek temples. 2 wonders for the price of 1. What it is a building in Edinburgh. It's a building which is the antithesis of Georgian or Greek architecture, full of its laws and its subtleties. It's a vile, disgusting, depressing pile of concrete. It's called the Appleton Tower. It's where I learned most of my undergraduate science. It was built in the 1960s by the University of Edinburgh in one of Edinburgh's finest squares, and it sits there like a great toad, sneering, insulting the square it's destroyed, and in fact insulting anybody who can bear to look at it. The first part of the wonder is that anybody ever allowed it to be built, and the second part is that it hasn't already been blown up. I must think that nails are pretty wonderful, because I've been working on them, I hate to admit, more or less non-stop for 30 years. I actually collect sort of plastic and pottery and steel images of the damn things. And some people would say it's become an obsession, but of course they're wrong. Like all the best wonders, I guess, it's still a mystery as to why they're so variable. But the thing I find extraordinary about these snails is that if you go into many parts of the countryside, and these things are common, they're not birds of paradise, they're everywhere. If you go into many different places and just go into a hedgerow or what have you and pull out a sample of snails, they're all the same species, same kind of snail, they can all interbreed. But as you can see, they all look different. Different colours, different numbers of stripes. In fact, I once worked out that there are about 18,000 different combinations of characters on the shell. And in any one population you would quite often find 100 animals, all of which are different. And all those differences are genetic. They're all under the control of DNA. And the question is, why are those differences there? Now, one might argue that it's not the world's most important question, why are snails different? I like it as a question, but that's my own little perversion. When we started working on them, the only way we could preserve them was to kill them. I mean, 20 years ago you didn't used to think that really was not really a very ecological thing to do. So I used to knock them off in thousands without batting an eyelid. Now I don't. I put them back alive whenever I can. I must say, when I see people picking them up in thousands, as they do in Spain, to eat them, maybe my conscience shouldn't be as tortured as it actually is. I don't actually eat them myself. Snails are constantly living on a thermal tightrope. They have to keep their temperature about right, and they do that by moving in and out of the sun. If you've ever sat on a black iron park bench in shorts on a sunny day, you will know within a few seconds that black objects heat up more than light objects in the sun, a lot more. So the short answer is the dark animals heat up more, absorb more solar energy than the light animals, and that explains why the dark genes are commoner in Scotland. So that's kind of trivial. That's bloody obvious, I hear the broad masses say. Did it take you 20 years to find that out? Well, not quite. But we're still left with the question, okay, all these snails, all the ones on this table, they came from a length of wall on the French-Spanish border last week, a length of wall probably 6 feet long, and yet they're all different. Can there be that much climate difference on that wall? Can they perceive it as being so different? What you need to know is what particular dose of sunshine every single snail is getting. So one day in Spain, I was wearing the pair of jeans which I had worn in the 60s, which had become very faded and blue, pale blue and patched. And it suddenly struck me that the reason why these jeans had become faded was that the pigment they were coloured with was cheap and it broke down in sunlight. The longer it spent in sunlight, the paler blue it became. So we had the answer. Immediate piece of gene manipulation, cut out some little bits of blue genes and glue them onto the snails, right? And put them in the sun, leave them go, and see whether the bits of blue gene on each snail faded to a different extent, depending on whether the snail was dark or light. Well, the short answer was that didn't work. That was just ridiculous. I'm vivid memories of a Spaniard walking past, picking up one of these things, looking at it with horror and sort of crossing himself and walking on. But we did actually go one step further, which was the answer, which was to take the blue pigment, which you use for colouring your trousers, your blue jeans with, take that, in fact have it made specially in a chemical factory, and mix it with a stable, ordinary yellow paint. Now blue and yellow make green, so we now had a green paint which we could put little spots on each snail, and the longer each snail spends in the sun, over a month, 2 months, 3 months, the more of the blue pigment in that paint breaks down, so the more the paint fades from green to yellow. So we did that, we marked thousands of snails, put them back into the natural habitat, and lo and behold, it turned out that the light ones and the dark ones, animals with different genes, spent quite different times in the sun. The dark ones spent their time in the shade, the light ones spent their time in the sun. So we sort of measured the habitat, the behaviour of individual animals over many, many months at a cost of effectively nothing. So that, I thought, I have to say, was rather a neat idea. And it's kind of a wonder, really, how that idea has been picked up and used in different ways. There's a chap in Africa who I happened to meet in the pub once, who was working on river flow in the desert, and he wanted to know how long each river was full of water, maybe only a few days a year. And so that was obviously important for irrigation and the like. And we were talking about this and that, and we had jointly had a brilliant idea, which was to take sticks, paint them with this fading paint, stick them in the bed of the river when it's dry, and when the river's running, the paint doesn't fade because the sun doesn't get in. When the river's dry, the paint does fade. So lo and behold, you don't have to be there. You just go there after a year, and the amount of fading tells you how many days the river's been full. So that was pretty clever, which is kind of a long-winded way of explaining why I think that these snails are really one of the 7 wonders of the world. Like a lot of biologists, I've always had a fear of physics. Certainly a fear of physicists as well, if the truth were told. But certainly a fear of the subject, because physics is basically hard, let's be frank about this. But when I was studying physics, one thing really struck me as incredibly clever, which was measuring the speed of light. Now that's a real wonder of the world. I mean, how can you possibly measure the speed of light? You must need all kinds of electronics and computers and God knows what. Well, in fact, it was done in the middle of the 19th century by a French physicist with a wonderful name. His name was Fizeau. I can sort of see him there with his beret and his bottle of champagne. And all he needed, actually, was a couple of mirrors, a couple of lenses. And what he did was to go to the Alps and take 2 mountains about 10 miles apart. And he stood at the top of one mountain with a very bright light, which he shone through a lens at another mountain, at a mirror, where it came bouncing back. Okay, so that's very simple. But the crucial part of his apparatus was a toothed wheel, a kind of cog wheel, which he could spin at different speeds, sometimes quite fast. And his clever trick was to shine pulses of light, or beams of light, through this wheel, through the cogs of this wheel, as it was spinning at different speeds. Now obviously if the wheel isn't going very fast, and the light sets off in one of the gaps between the cogs, it goes off to the other mountain and back again without any trouble. It just comes back. You get a reflection back in the apparatus. But as the wheel goes faster and faster, the light of course does take a certain amount of time to travel that 20 miles. And if the cog wheel is going faster and faster, suddenly you get to a situation where the cog, the obstruction part of the wheel, the black part of the wheel, interrupts the light beam as it comes back. Okay? The wheel is going so fast that the cog has actually broken the beam. So suddenly you don't get, in the apparatus, the light coming back. It's been interrupted. Now you can work out the speed of the light. All you need to know is the distance between the two mountains, the speed at which the cog is travelling, which gives you the time it takes for the cog to get into the path of the returning light, and suddenly, fizzo, you've got the speed of light. And old fizzo got it about right, which I think is pretty impressive with a piece of apparatus which you could probably make nowadays for a couple of £100. Measuring the speed of light is a classic of the finest kind of scientific experiment, and the best experiments are summed up by one word, which is cheap. Why did I become a biologist? It's very hard to know. I mean, I was told several times when I was at school that I shouldn't be doing sciences, I should be doing the arts, I should be doing English in particular. And I had the common sense to think, English, English degree equals bank manager. And I thought, not interested. I'd much rather be doing something which is, real. Beauty to me of science, and I really do mean it, is that science is the art of the mediocre. Anybody can do science. Now, I'm very much a second-rate scientist, but everything I do on those snails, for example, is novel. Nobody's done it before. It's only a tiny advance. It's scarcely an advance at all in biology. It'll probably be forgotten in a few years, but it's an advance. Now, I defy 99.9% of arts graduates to say that anything they've done in their careers advances the cause of the arts in any creative way at all. And in fact, I would argue that many people who do advance the cause of the arts, many authors, many musicians, don't in fact. The reason they do that is that because they're extraordinarily clever and able. It's got nothing to do with the fact that they did arts at school or at university. Science isn't like that. Science is for everybody. And if you don't think you're a genius, be a scientist.